Okay, so we have look at example on the line integral for vector function. Okay, so as I mentioned before, one of the application of the line integral for the vector function is to compute the work done if the vector function given is considered as a force field. Okay, for example, in general, the definition of the work done as a work done is a line integral if we are given the vector field f over a smooth curve rt, okay, given by in the vector function t from a to b. So the work done is given by the line integral if for the given vector field. Okay, so we look at example, the next example. So I call this as example, before this we have example 3, so this is example 4. Okay, we have an object moved in the force field given counterclockwise from the point to 0 along the elliptical path given by the equation here to the -0, and then back to the point to 0 along the x-axis. So it looks like we have a closed curve, right? Because the starting point and the terminal point is the same. So for this, okay, so elliptical path is given by the equation of x squared plus 4y squared equal to 4. So we know this one is supposed to be an ellipse. Okay, so when we sketch, so so this one is 1 and 2. So this is 1 and this is 2. That is the ellipse given by the equation on y-axis plane. Okay, so now based on the instruction here, the starting point is at 2, 0. And it's traveled to the -2, 0 along the elliptical path, which is this way, and back to the point 2, 0 along the x-axis. So we have x-axis here. Okay, so meaning that this one is not part of the curve. Okay, so now it looks like we have two curves, right? So this one C1 and this C2. Okay, so we want to evaluate the work done given by the force field. So we know that the formula of the work done, W, along the curve is given by F dot dr. Since we have two curves, then it looks like we have to compute them separately along C1 and along C2. Okay, look at the C1. The C1 is based on the equation here. Based on the equation, ellipse equation here. Okay, so it looks like you have to convert into a parametric equation, okay, or provide the RT for the C1. Okay, now we focus on the C1 to obtain the C1. To obtain the C1, so based on that equation, it's just like a circle which means that you have to use the trigonometric identity, right? So just like a polar or circle, so we take that idea to find out what is the parametric equation for the ellipse. So as we know that okay, so we just look at the identity trigo. The possible identity trigo that can be used here is cos square t plus sine square t equal to 1. Why I'm taking that one? Because it looks like something square plus something square is equal to 1. So they have a same pattern, right? So what we can see here, this one is x squared over 4 and this one is y squared, right? So now we want to get just x, so x over 4, sorry, just a square root, so x over 2 is equal to cos t and then y equal to sine t. So because we need only x, so x equal to 2 cos t and then y equal to sine t. So that is the parametric equation for the C1. Okay. So now we want to okay, based on the information provided, the f given is y square and then 2 x plus 1 y. Okay, and dr containing the dx and dy. Okay, so now for the C1, okay, now we work on the C1 only. Okay, so f dot dr for C1, then we have y square dr dx plus 2y x plus 1 dy. Okay, so dx dy mean we have to differentiate. So from here you can determine the dx is differentiation respect to t. So minus 2 sine t dt. And then dy is cos t dt. So we can substitute. So what y squared is sine square t, and then dx is negative 2 sine t dt, and then 2y, so 2 sine t, and then 2 cos t plus 1. Cos t dt. Okay, so then we have to simplify. So we have negative 2 sine cube t, and because they are all t, so we can join them together. So we have plus 2 sine t plus 4 cos t sine t dt. Okay, so then in order for us to determine to integrate, we need to determine the limit. Okay, so based on the x and the y that we obtain, so Okay, maybe I have to rewrite into a proper way. So 2 cos t sine t. So so we have to find out, so what is the t, so that the point that we have is at 2 and then 0. It looks like you have to determine the possible t so that the sine t 0 and the cos t becomes 1. Okay, so it looks like the possible t is t equal to 0, right? So when you have t0, when you have the point of 2, 0, so your r is at 0. Sorry, your t is at 0. So your initial value is t equal to 0. And then we want it to be minus 2. Okay, now you have to determine for what t, so that you have minus 1. Yeah, the cos, something cos, and then you will get minus 1. And then the t is also, sorry, the sine t then becomes 0. So it looks like the possible t is pi, right? The possible t is pi. So that when sine pi is 0, cos pi is minus 1. So now when t is pi, then you will get that value. So now that is your upper limit of t. So now we have to integrate them. For me, this is not so direct. So this one may be direct. This one you have to use the identity of trigonometric. And this one also you need to use the identity of trigo. I realized I've forgotten to multiply this one with the cos t as well. So it looks like I have to correct my answer here. So 2 sine t cos t plus 4 sine t cos square t dt. Okay, so I'm not going to solve this in detail, but I just give you some hint. So for this one, you have to use your identity. This one also identity, and this one we can use a substitution u equal to cos t, so that the sine t here can be cancelled out. Okay, so here for the sine cube here, what we can do is when we reduce the powers, so we have sine t multiplied by sine square, and then I'm using the identity of trigo, 1 minus cos t. So and then I plug it back into this one, so I have this one, and this does not change. But when can you see that they are related to each other, right? So there is cos squared, and this is also cos, and this is cos squared. And it looks like we can apply the direct substitution for all the 3 terms here, 1, 2, and 3 for the same u. So when I just let u equal to cos t, and then the sine t outside here, the sine t over here, and the sine t over here can be cancelled out. Okay, so we have to transform everything in terms of u. So I differentiate u respect to t. So I have minus sine t. So I just bring the dt over here, so that I can just straight away obtain that the sine t dt is equal to minus du. So when we substitute the sine t dt and the u equal to cos t, and this is the simplified version. Okay, and then when we expand and simplify, finally we can easily integrate with respect to u. And don't forget to be careful with the limit. The limit 0 to pi is only for t. If you want to use the t 0 to pi, then you have to replace back the u in terms of t, or you can just evaluate based on the t from 0 to pi. Then you can find the limit of lower bound based on the lower bound t0, and what is the value of u based on here, or you can just use this one. Okay, so then it looks like it is there are many terms. Then be careful when you replace the value. So it looks like the final answer is 0. Okay, so what we can see that the work done, okay, when we refer to this one, the work done along the C1. So this one only for the C1. We don't yet evaluate the C2. So for the C1 only, the work done is 0. So that is possible, ya. Pak you macam buat kerja tapi end up 0. Okay, and then C2. So C2, now we work on C2. C2 is just a segment line, a line segment. Okay, so joining, so now we work on this C2, f dot dr, C2. So C2, we have a segment line or line segment from, we have sketched just now, right? Minus 2 to 2. So minus 2, 0 to 2, 0. So meaning that the only changing is x. Y does not change. Okay. So for this one, we know that the equation for this line segment is y equal to 0, because this one is located at the x-axis, or you can see here the y does not change. Then we can see that the y equal to 0, and we have dy equal to 0. So now when we look at the f dot dr, where we have this one. Okay, so now y squared dx. Okay, so firstly I have to replace one first. Okay, y squared dx plus 2y x plus 1 dy. Okay, based on the information that we have here, then we can see that y is 0. Okay, so 0 dx plus and dy is 0. So dy 0 meaning nothing, right? And then we have 0 dx when we integrate. And we know that for line integral here, we should have the definite integral where there is a limit, but in this case the limit is unneeded, so you don't need to, actually you can find it directly, right? So the only changing is x, so x is from minus 2 to 2, and since minus 2 to 2, when you integrate 0, the answer is constant, right? Minus 2 to 2, but because a constant, so you still have a minus a, and then end up to be 0. So your work done along the C2 also 0. So as a total, the total work done along the C, where C is the combination of the C1 and C2 for the given vector field, is 0. Okay, not always 0. Okay, so it's not necessarily if you have a closed curve. So this one is a closed curve because you start and back to the same point. It's not necessarily 0, but in this case it is 0. There is a reason why it is 0. Okay, I will explain to you on the next section. Okay, so actually the step is provided. Okay, so there is the summary of the line integral that we have done so far. Okay, so for this one, work done or line integral for vector field, so you have to be noted that we always use this one. So this one is the simplified version of this f dot t, as I mentioned before. And similarly for this one, so all these are then is already simplified into f dot dr, and f dot dr is simplified into this one. So this one actually there is dz at the back here. It's missing. Should be dz over here. There should be dz. Sorry. Should be this. Z. Okay. So this is the thing. F dot dr. The f dot dr then become this one, the common form. Okay.